Thank you, everyone, for coming. This is joint work with Howie Shrobe and Boris Katz at MIT. It's part of a new ONR project we just launched. And the challenge we're looking at is that there's many activities that the people carry out that involve executing complex procedures. And historically, those have required long and arduous training. When we talk about expertise, often we're talking about expertise in some kind of sequential goal-directed activity. Now, there are two classic ways of trying to use AI to automate those activities. The earliest one was expert systems, where you would build knowledge bases manually, often by observing or interacting with an expert. That worked very well. It was very successful, but it was slow and expensive. More recently, there's been a lot of excitement about learning control policies from using things like reinforcement learning, but that requires extensive runs in simulators, and we don't always have simulators for many real-world tasks. We need a more effective approach. This is the classic problem of the knowledge acquisition bottleneck, and neither of these previous solutions are really viable as broadly as we would like. The good news is that we already have an important source of information that we can use. It's instruction manuals. And if we could find a way to take those and turn them into procedures, then everything would be cool. Well, here's a recipe, just to give you a simple example, although it's not as simple as it may seem, about how to cook a meal, particularly a ham omelet. So this says to make a ham omelet, break 3 eggs into a bowl, stir the eggs until they are smooth, chop some ham into pieces, put the eggs in a hot skillet, fry them until they're firm, add ham and some grated cheese, fold the omelet in the skillet, and then fry it for 2 more minutes. And what we want to do is transform this text into some kind of explicit encoding of the conditional procedure that it's describing. Now, there's a very thick book that Newell and Simon published in 1972 called Human Problem Solving. In it they give lots of examples of the stages that you should go through, that they thought you should go through to develop computational models of complex cognition. And the very first step is called task analysis, and that's where you look at the problem you're trying to solve, and you look at different ways to approach it, including how you would represent states and goals and activities, what problem spaces you might search to find solutions, and heuristics for exploring those spaces effectively. A task analysis like this always precedes your system implementation. Okay, and in fact, today I'm not going to talk about an implemented system, but it does lay necessary groundwork. And let me point out something to the reviewer who generally liked the paper, but asked, well, how can you do a cognitive task analysis without having data about human behavior? So this is supposed to happen before you collect the data, if you were trying to model human cognition. The word cognitive here does not and has never meant human or psychological. It means thinking. So this is an analysis of cognition, of the cognitive task. Okay? Now, an obvious thing to do is to try and break this into problems, and there are 3 natural subproblems of procedure acquisition. The first is to go from the text to come up to parse your sentences syntactically. From those, you try to extract the meaning structures using some kind of semantic processing. And from those, you try to analyze the meaning structures to figure out the organization and details of the stored procedures. Now, this is what is sometimes called a pipeline architecture. It has well-known limitations. I don't think it's completely right, but it's a good starting point. And don't forget one of Simon's main messages to our community. Complex cognitive processes are nearly decomposable. Not fully decomposable, but but you can look at them by breaking them into pieces, and then the interactions among the pieces will be reasonably minor. I know there are people in the audience, including Sergey and Marge, who will probably disagree with that on the language side. That's okay. But let me continue with the story and we'll see how it goes. Now, task analysis isn't from scratch. It's always done in the context of some theoretical framework. And in this case, we're going to assume that our procedural knowledge is modular in the sense that the elements can be composed as needed, relational in the sense that each element describes some configuration, causal in the sense that it describes the effects of actions under certain conditions. It's hierarchical in that it breaks activities down into components, and it's disjunctive in that it can specify different ways to address the same task. So all of these postulates are consistent with what we know about how humans encode procedural knowledge. And fortunately, there's a representation that is well known in our community called hierarchical task networks that satisfies those constraints. Just to review briefly, an HTN encodes procedures as a set of methods. Similar, they look a little bit like prologue clauses, a little more structured. Each of them has a task name and arguments that the task takes. Conditions under which, so these are each set of methods. Each method has a task name and arguments. It has conditions under which that method applies. It specifies a sequence of component subtasks that you would typically do in order. And optionally, it can specify the effects of that method's application. That may be incomplete, particularly if you have like recursive methods, but that's okay because you can still have useful information there. Again, so HTNs are a rich way of specifying procedural knowledge. They can encode conditional, disjunctive, and even recursive procedures, and they have been used in the literature not only for generating plans, but also for executing them and for plan understanding, all in the context of goal-directed activities. It's a little ironic because HTNs often don't make goals explicit, but that doesn't mean you can't, and they certainly are goal relevant. Now, we need principles of learning to constrain how you acquire these structures, and we're going to assume 4 key constraints here. One is that learning is incremental, and that the modular elements are acquired from successive experiences. That could be individual statements in a text, or it could be sequences of instructional text. It's inherently abductive in that it's building on existing structures and trying to come up with some kind of explanation in terms of those existing structures. It's cumulative in that later learning builds on earlier ones, and it's inherently rapid. That is, it's going to acquire complex structures from relatively few items. We're not going to have to read many recipes to learn how to make a ham omelet. We'll get it from a single recipe. And again, these are consistent with well-known results about the nature of human learning. Now, let me go through the 3 stages in more detail. And in each case, I'm going to specify what the task is in terms of inputs and outputs. And this is something I recommend to everyone in the community. I think it's really good to describe both for your overall problem and in terms of the subproblems, what the problem is in these abstract terms. So syntactic processing, you're given sentences, again, that are describing, in this case, complex procedures like recipes. You're given grammatical knowledge about the ways that sentences are organized, can be organized. You also have lexical knowledge about the words that can occur in those sentences. And the output of this for any individual sentence is going to be a parse tree or some kind of description of the syntactic organization of the sentence. Now, the good news is that formal instructions, like recipes, typically follow the rules of grammar. So it's not like dealing with spoken language where there's lots of disfluencies. That simplifies the task considerably. And that opens the door to using systems like START. This is a system that Boris Katz has been working on at MIT for about 30 years. START is a a parsing system that covers a wide range of English constructions, has a very broad lexicon with different word senses. The output is a set of nested triples. I'll show you an example in a second, but every triple has a subject, relation, and object. It does, even though it's a fairly shallow, quite shallow parser, it does handle reference resolution across sentences. But it does other things, delays other things. It will not, for example, attach prepositional phrases. This is one of the big sources of ambiguity in syntactic parsing. So start's been used in a bunch of applications, including phone interfaces, question answering systems, and design assistants. Here's an example. Remember, here are the first three sentences in that omelet recipe. And here are the start triples that are produced in each case. Okay, so U is implicit in each of these. U is the agent. So U break 3 is a token for the type relation, the relation break, which isn't shown explicitly here. Eggs 1 is a token for the word eggs. If you had 2 eggs in here, then there would be an eggs 2 as well, and they would be distinguished. Stir the eggs until they're smooth. You'll see this is the same token here, eggs 1, that appears in many places. So start is resolving that reference, but it's not. But again, there's other things it will refuse to do because it's conservative, and leaves that for later stages. And it has things like quantifiers and properties of small and so on. If you drew this as a graph, there would be looks like a semantic network, but there would be arrows coming off of some of the links themselves because they are themselves tokens. The second step is semantic processing, where you want to transform those parses into something that represents meaning. So again, the input is the parses of sentences like we just saw. You have background knowledge that maps parses onto relational meaning structures, and also that maps words onto available concepts. And the output is a set of linked semantic relations that specify meanings. Now, there are different ways to do this. We heard about conceptual dependency a few days ago. Another one that has been widely used is called case frames by Fillmore. And this will look familiar to you because when I'll show you an example, because it maps directly onto to predicate logic. So one promising interpreter that's around these days is called Genesis. You heard Dylan Holmes talk about that in the Winston Symposium yesterday. That's work they did together. That's actually already integrated with Start, and it inputs one of its inputs is parses generated by Start, these triples, and it has a set of rules that will match against sets of those triples in certain configurations, and say, oh, this fits into this. I can use this to populate this case frame, like this breaking, the frame for break, and it would recognize that. And the breaking isn't just about these two things, but some other elements too. And it also it has access to WordNet, which lets it do things like handle synonyms and put them into canonical encodings. So Genesis does other things too. This is actually just about halfway through what Genesis does, but it produces semantic structures that can be used for summarization, question answering, and other tasks like the one we're talking about. So here's the kind of output that Genesis would produce along the way. And if you see on the left column, you see a sequence of activities, actions, like you break these eggs into a bowl. Again, these are case frames that would actually have slot names for agent, object, location, and so on. Those, I didn't have space for those, so I didn't put them here. But this looks like a plan, right? It's a sequence of actions, of operators with arguments to them. And then there's state changes that result on the right column Like after you break the eggs are in the bowl. After you stir them, they are smooth. After you chop the ham, notice there's a new symbol there, pieces one, which wasn't there before. That's something that's actually produced by chopping. That's not an argument to chop, but it's a result. There's a hot skillet, and so on down, right? So this is, and I haven't shown you the entire state because mostly the state changes the same. There's an initial state. Some things remain the same, like you have a skillet and it's still a skillet. But there's an evolution of the situation as you go along, as you carry out these activities. And notice, again, that the recipe did not actually state all the actions explicitly. It said to put the ham pieces in a hot, to put the eggs into a hot skillet. And it didn't say anything about heating the skillet. So that's not there. And Genesis would not actually produce that in this pass. But so that's an issue. Okay. Now the third stage is to construct procedures, and we want to translate meaning representations into procedural knowledge. Again, we're given the states that you go through and the sequence of actions, both partial possibly. We have knowledge about component procedures, the things we already know about. And we want to produce some kind of a hierarchical procedure, actually an HTN, that doesn't just specify the hierarchical decomposition, but also the conditions and effects of each of the methods. That is the classic problem of learning HTNs from sample solutions. And in fact, I've done some work on that with Negan Najati, did her thesis on that with me, and Nan Lee did some work. It's all embedded in an architecture called ICARUS that Donkyu and Choi and I have described. And you're given, the system takes a sequence of actions and background knowledge. It analyzes them in terms of how they achieve the goal description, using a variant on means-ends analysis to reason backwards. And a little known fact is that means-ends analysis actually searches a space of problem decompositions. So when you're done, you have a decomposition hierarchy that you can turn directly into a set of HTN methods. And then you have to go through and identify conditions and effects. We use something similar to explanation-based learning, but a little bit it comes up with more general conditions. And the key question is, when do you decide to give two methods the same task name? And the answer is when they achieve the same goal type. I won't go into the details, but this approach, we've shown that it's incremental, it's cumulative, and it's very rapid. And this is the kind of output you would want for that omelet recipe. This is breaking, you have a high level task, make ham omelet. It's got 3 subtasks, and each of those has subtasks as well. Now this is just showing the structure. This is not showing the conditions on the methods or their effects. That would be in there too. I just don't have time to go over it. Right, so we have some existing systems that we could use. None of them are as complete as we would want. We need to extend them in various ways. In particular, start I'd say is the most mature and most robust. And so mostly it's a question of adding knowledge to start, including specialized constructions that can appear, and like in recipes. So things like add the ham and grated cheese. The and there actually usually means do them in that order, even though it doesn't particularly say that. Or instructions like as, yep.
1 minute, please.
Right. As the potatoes brown is a slightly strange construction there, because we think of, but you could easily modify start to handle that. And then there's unfamiliar word senses. I would never use the word whisk, but it has a specific meaning in here. I think of it as a noun, but it's a verb here, and top is a verb too. Top with spinach mixture. So start makes it pretty easy to add these constructions and lexical items. I think we need more extensions to the Genesis system. We need to augment its case frames to include the conditions and effects on actions and methods. It also will lack some knowledge for the particular domain, so we need to tell it, give it the ability, if it gets stuck, to come up to a user and say, hey, I don't know what to do with these syntactic triples. Can you give me a rule to help me turn into a case frame? We also need to give it more generic knowledge about things like opening containers, filling them, heating them. And right now, my understanding is Genesis generates a single interpretation. Sometimes there's ambiguity, and you really want to keep multiple hypotheses around and resolve them later. And there are plenty of things we need to do to extend the ICARUS learner, including adding the ability to infer omitting actions. Sometimes if actions are omitted, you can figure out where they are because you need them in order to hook the chains together. To infer missing conditions. If you find a step that seems to not be there to achieve some condition on something that you didn't know about, or filling in the effects of conditions that are needed for later steps. And there's sometimes you'll have instructions that have extraneous actions. You want to ignore them because they just don't contribute to the goal. So each of these would involve using constrained means ends analysis to connect portions of the solution trace. It's not, you just don't assume it's all there, but it's also, you also don't have to search from scratch because it's highly constrained by the steps you know about. So last slide. This cognitive task analysis is just the first step. We still need to implement an integrated procedure learner that does this. That means extending Start, Genesis, and ICARUS in the ways I described, but all them into an integrated system, initially with that pipeline architecture I showed you, but maybe something better later. We need to collect test cases of complex instructions, recipes, they're all over the place, and we'll get them. We're also looking at repair manuals for shipboard equipment. And we also need to evaluate the system's behavior experimentally. We need to specify our measures of success, things like the ability to, if you know ahead of time what the target HTN should be, you can actually get things like precision and recall. But you also want to combine this with a performance element and actually show they can carry this out in a low fidelity simulated environment. And we also want to systematically vary the difficulty of the task. We want to do things like take out things in the instructions and see how well the system can handle that anyway. That is, can it infer the missing steps, the missing conditions, and so on. Together, these should let us demonstrate and understand the acquisition procedures for written instruction. And stay tuned. We hope to have some more impressive results next year. Thank you.
Thank you very much, Pat. There are some questions on the Slack channel. This question is from Karen Myers. Recipes and other types of procedural descriptions often include important non-performative information that doesn't map well into HTNs, such as constraints, diagnostics, warnings, suggestions. Have you thought about how you would represent that type of information?
Well, I'd love to see some examples. I agree in principle, but without examples, I'm struggling to come up with one. Can you think of anything? I mean, just to be clear, one of the reasons there has been a tension in the community, people who work on learning procedures. In fact, it's not surprising this question came from Karen because she works with a framework that's similar in spirit to HTNs, but actually has a richer representation of procedures. I favor HTNs for the reason that people favor inductive logic programming, favor Prolog, is because it's very constrained and still takes you a long ways. So it's possible that we'll hit snags that we can't handle this way. Certainly there are things like partial orderings that are easily put into HTNs, right? Certainly you can stick in things like timing information. Those aren't hard, but the things Karen points out, I'm less sure about. Maybe we should take it offline. I think it's a legitimate question.
What about structural constraints like something should be made of ceramic and not metal?
Well, that's just a condition on a method.
Okay.
Yeah.
Now, Ken Forbes asks a question building on Karen's question. Michael Beat's group reads recipes from the web using QP theory as intermediate representations for the processes involved in cooking, which are then executed by their robots. Have you thought about using qualitative models as part of the semantics that helps explain why these steps in the procedures are needed?
Well, yes. I mean, certainly, just for the record, I've always liked Ken's work on qualitative process theory. I like Michael Beats's use of it for. I mean, I didn't mention that work, and I didn't even think of it. I'm glad Ken mentioned it because it's so focused on actually building robots that do things in the physical world, and our application is very, very different. But it is very relevant. And just for the record, if you have hierarchical task networks or any kind of planning representation, I mean, those are qualitative. They do have something like qualitative physics. It doesn't have support the kind of continuity that QP theory does, and I am a fan of that. In fact, one of the people on our team, Gary Borchardt, who spoke yesterday, actually, you saw that he in his work on transition spaces is very much into that kind of representation. We certainly want that. I believe in describing action models that talk about continuous change, but at a qualitative level. So I'm sympathetic with the idea. I probably wouldn't use QP theory itself, but something similar. Yes.
Couple of questions, one from Sergey, another from Marge, to sort of kind of build on each other. Sergey is saying, so you constrain ambiguity in inputs. For example, in pieces 1, X1 does not refer to a piece of music or many other senses of a piece. Then Marge says WordNet can end up ambiguating more than helping it disambiguate. Any thoughts on that?
I'm not an expert on WordNet, and I'm not even sure the details of how Genesis uses it. But it's clear that I don't think that the pieces thing there, I don't think is an issue, because in the context of we're always talking about what's happening in this particular set of instructions, right? And so if there are different, if you had different knowledge elements that would talk about different kinds of pieces that occur in different case frames, then I think it's going the context of the instructions is going to constrain that a lot. As to the details of disambiguation, you're going to have to wait until next year when we have a implemented system, and maybe somebody who knows more about the Genesis innards can tell you about that. They're legitimate issues. Remember, this is a task analysis and not a running system. So I fully expect that we will have to address some of these issues.
So time for one more quick question. I think Karen amplifies her question. She's giving an example of the kind of constraints that can occur that HTN may not be able to represent well. Yep. So an example is, don't overheat the eggs.
Yes. So you certainly can say that in a different way that doesn't sound like that kind of constraint, but that doesn't mean that something stated that way won't be part of the framework. I think that does require an extension to HTNs. I've thought about that over the years. I think that it's worth it, and I look forward to talking with Karen about how to extend the representation. What I am reluctant to do is any change we add to the representation has to be limited, and it has to be learnable, representable in a modular way and learnable in an incremental manner. Otherwise, we're going to lose all the advantages of HTNs to begin with. But I'm fine with that. Thank you very much.
Thank you, Pat.